Thanks for joining me. My name is Matthew, and in this video I'm going to talk to you about the hyperbola. The hyperbola is a set of points that we saw in the previous video can be created by taking a plane and slicing through a pair of stacked right circular cones. But it also happens that if you take the distance from one of the foci, so from a focus to a point on the hyperbola, and the distance, what's happening? My pen was not enabled, sorry. So if we take this first distance from a focus like F2 to our point P, and we take the other distance from the other focus to our point P, the distances from those two fixed points is going to be a constant. A set of points in a plane, the difference of whose distances. So d2 minus d1 is always going to be the same value. Interesting, I suppose. I wonder what d2 minus d1 is going to be. If we took these, let's just take this distance here from F1 to this kind of vertex looking point that's right here, or sorry, F2 to that vertex point, and then on the left there's this focus 1, so from there to this vertex here. And what if our point P, what if we dragged point P down this parabola and actually put point P right here at this vertex? Then D1 would be this distance right here. D2 would go from focus 1 all the way over here to that vertex. So that distance d2 would actually include this little distance from the focus to the vertex, this one. I think that d2 minus d1 is going to end up equaling this distance right here, the distance between the vertices of either half of this hyperbola. That's my guess anyway. We'll see if that's how it plays out. Standard form of a hyperbola. I'm laughing in strange ways. A, because I'm tired, and B, because this is like totally backwards from what we just saw with the ellipse in the previous video. In the first equation, x squared and y squared in the numerators in the typical order. In the second equation, over here we see y squared in the first numerator and x squared in the second one. That's backwards. These fractions are being separated by a minus sign. For an ellipse, it was a plus sign. So sometimes the numerators are going to look like they did for an ellipse, and sometimes they'll be backwards. These are always going to be separated by a minus sign, and look what happens this time. A squared, b squared, a squared, b squared. Now the denominators aren't moving? Are you kidding me? So frustrating. Well, let's see how these equations match up to some labeled graphs like we saw with the ellipse. Okay, actually we don't even need to be up there. The only thing that's in the blue box that's at the top of the screen that you need to pay really close attention to is this relationship. So we're using a slightly different relationship this time in order to calculate the distance from the center to the foci. Still the c value, but it's calculated this time by doing a squared plus b squared instead of a squared minus b squared. C squared equals a squared plus b squared. That's a plus sign, and this is a minus sign. They're opposite one another. it was the same way with the ellipse. The ellipse had a plus sign in its primary equation, but it had a minus sign in the equation to help calculate the distance from the center to the foci. Okay, just trying to point out all the patterns that I can, and then you do with them what you will. So other than c squared equals a squared plus b squared, I'm going to slide that box off the screen a little bit so I can zoom in on these graphs. And what are we seeing here? All right, so I'm looking at this equation down here, and I see that under the x squared, there's an a squared. And then in my graph, in the horizontal direction, sure enough, from the center over to this vertex, it's a distance of a. So it's sort of like a horizontal radius, but it's sort of not. It's not really a radius because it's not inside of a circle or an ellipse. Hi, yes, I'm in here. Such a loudmouth. Sophie's so loud. And then what about in the vertical direction? I'm not seeing the denominator in this fraction. I'm not seeing the b value appear anywhere in this graph. The thing that I am seeing, however, is the c value. So there's that distance from the center to the focus. That's my c value. Okay, well, all right, so we don't know about the b value yet. Maybe we're only using the b value in order to calculate the distance from the center to the focus. That's not true, but at the moment, that's what it looks like. Okay, and then what about in this equation and this graph over here? Here, this equation is leading with the y squared, and under the y squared is the a squared, and yeah, okay, so this time it's a vertical distance, radius, kind of, not really. And the c value is there, right? So we do still have that distance from the center to the foci, up and down. Oh, here's another sort of characteristic that might be of assistance. This equation on the left leads with an x squared, and the concavity of these two curves, they are concave in the horizontal direction, the x direction. This equation on the right, leads with a y squared, and it's concave in the vertical up and down direction. Maybe that will help us when it comes time to play a matching game or something like that. I think those are all the things I want to point out to you in those diagrams. So let's try to, hey, a matching game, what do you know? This equation leads with an x squared, so our curves must be concave in the x or horizontal direction. So it has to be, it's got to be one of these two, okay? And then in the x direction, the square root of its denominator, so the square root of 4, is 2, and that was sort of that horizontal radius. So that distance of 2 is right here. Right, so that's how I'm identifying it. Those are, I'm not going to go through the process of calculating the foci in order to try to help decide which graph matches up with which equation. Well, the foci are a little tough to see, but, oh, which is a little bit punny because the c value, right? The distance to the, hard to see. Anyway. So I'm just using concavity and that sort of radius idea that takes me from the center to a vertex. Let's look at the next one. This one also leads with an x squared, so obviously we know which one it is. But in the x direction, here's this value of 1, right? So I'm taking the 1, I'm square rooting the 1 and getting 1. That should be my horizontal distance from the center to a vertex. And it sure is. Let's look at the next one. Y squared, so it's got to be concave in the vertical direction. Denominator of 4. So we take the 4, We'll square root it. We get 2. That should be our vertical distance from the center to a vertex. And a distance of 2, okay? So that's going to be... I'm just switching colors, circling it in red so that I can take it over here. And finally, leading with a y squared has to be concave in the vertical direction. Denominator is equal to 1. We take the 1, we square root it, we get 1, and that'll be our vertical distance from the center to the vertex. This isn't so bad, right? We can do this. Find the standard form of the equation of the hyperbola. Okay, I'm scared again. I always try to put myself in your shoes when I'm working these problems. I try to think, well, what order would they think of the steps of these processes? What's a tool that they could have to start with consistently that they might get used to, and it would always help them arrive at the right solution. And you know that I like to draw diagrams, for one. The other thing that might benefit you in these sections where we're looking at these conic sections is to write down the general format of what the standard form of the equation is supposed to look like for a hyperbola. Right? If you give yourself sort of a fill-in-the-blank situation, it gives you some targets to aim at, and that might help you get where you want to go. So in this case, I'm going to plot some points first. I've got to go up and down 6 to the foci. I need to go up and down 2 to the vertices. Okay, so this one's pretty tall. I'm going up 1, 2, 3, 4, 5, 6, down 1, 2, 3, 4, 5, 6, and the foci are at plus or minus 6. There we go. And the vertices plus or minus 2. There they are. Now the vertices, the curve is actually going to pass through those points. And, oh, I just thought of a great analogy. I wonder if I should actually do this. It's not really the right style, the one that I have. Here's what I'm thinking, though. I've taught this course so many times before I started recording these videos, and just now did this come to my mind. I normally describe a focus as like the headlight, the actual bulb inside of a headlight, or a flashlight, or the receiver that's in the middle of a satellite dish, okay, sort of floating there in the middle of it. And then it occurred to me that when I look at these vertices and foci, I already know that this curve is going to be fairly narrow, I guess you could say. I know it's going to look like this. And the reason that I know that, or I think I know that, I don't actually know that. I didn't graph it or anything in advance, but my guess is that it looks like this. And I'm going to graph it on my grapher, and we'll see. It's because of how far away the focus is from the vertex. Look at this. The focus is 4 units away from the vertex. The vertices themselves are only 2 units away from the center, so that's a big difference, right? This distance right here is 2, and this distance here is 4. That's pretty dramatic, right? It's double. It's pretty dramatic. It just occurred to me that on a traditional umbrella, not the one that has like 3 folds in it so that it becomes so small that you can tuck it into your side of your backpack or something like that, but a traditional umbrella that's pretty tall, like a golf umbrella. I'm in Southwest Florida, so golf umbrellas, that's an easy go-to for us down here. But if you take a traditional umbrella and you're going to open it, you have to grab the handle with one hand, and then you grab this little thing that's going to slide up the stem of the umbrella, and you push it out away from you, And as you push it away from you, the umbrella obviously opens and gets umbrella shaped, okay? Now the vertex of the umbrella, if you close the umbrella again, the vertex is the part that you can imagine like jousting somebody with, or pointing at something with it. It's the end that you would tap on the ground while you're holding the handle. That's the vertex. So when you go to open the umbrella and you slide this little mechanism away from you in order to make the umbrella larger, the umbrella changes from a shape like this when the handle is right here. And as you push this little slide up and away from you, the umbrella gets wider, right? So now the slide is about here. And then the ultimate coverage happens when the handle is here and the stem of it is here, and you get that really nice umbrella shape that's going to protect you from the rain. And where's the slide at this point? You got these little support pieces that are coming down in here. The slide is way up here. Really far away from the handle, but really close. Here's the vertex. Here's the handle, or here's that little sliding stem. Look how small that distance is right there compared to when it was closed. Right up at the top of your screen, there's the vertex, and then here's the little slidey thing, and look at what a long distance this is. And look how narrow the umbrella is. Whereas when they're closer, like here, look how wide the umbrella is. That's why I think, since these are still pretty far away from each other, like an umbrella that's mostly closed, I think it's going to be pretty narrow. I'm going to grab my TI-84 grapher and, oh, and I can't type this thing into a graphing calculator. You must have to go into Desmos and do it. Let me punch it in. Okay, so before I can type that in and see what the graph looks like, I need an equation for it, which means we have some more calculations to do. So let me erase my umbrellas, and then we'll see if that suspicion was actually correct. Okay, so let's write down the sort of fill-in-the-blank skeleton of what this thing is supposed to look like. It's concave in the vertical direction, so I know that it's going to have a y squared in the numerator. The center is at 0, 0, so I don't have to worry about h and k just yet. The denominator under y squared is the vertical radius, or vertical distance in this case, from the center to the vertex, which in this case is 2. And we're going to take that 2 and we're going to square it. Minus x squared over b squared, a squared, I don't know, whatever you want to call it, I don't care, equals 1. Now how am I supposed to find this value? We're going to use our c value to help find that value. So c squared equals a squared plus b squared. I don't know what that was. It's supposed to be an arrow. C in this case is equal to 6. So we have 6 squared equals 2 squared plus, I guess we'll call it b squared. And if we subtract 4 from both sides, we get a 32 on the left-hand side. So 32 equals b squared, which means that this denominator is 32. So that's where that came from. Now this is an equation that I could type into Desmos, or depending on how fancy your calculator is, maybe you can punch it into your calculator. So let's see if my suspicion was correct. Where is my, oh, my equation is behind my head. Y squared minus 4, or sorry, y squared over 4 minus x squared over 32 equals 1. I'm pretty sure that's what our equation said. Over 4 and over 32, sure enough. And so my suspicion was the opposite was of correct. I guess the opposite of correct is incorrect, which would be wrong. So maybe that's a relationship that we can look for as we move forward and see some other examples of these graphs, I would like to know if maybe there's a ratio that we could learn about that would help us determine a little more accurately and in advance what our graph is going to look like. So let's keep going and find out. Let's go back into the notes here and find the standard form of the equation. Well, that's it. You're looking at it. Oops, we have to include the 1, however. There you go, there's your answer. Graphing hyperbolas centered at the origin. Okay, so we've been doing that. And then what we have not done, however, is what is happening here? Use dashed lines. What? To draw a rectangle centered at the origin with both sides parallel to the axes, one at plus or minus. So you can read through that. I already know what they're trying to communicate. So let me show you what it is they're trying to communicate there. And for a hyperbola that's centered at the origin, you could use what is in this blue box right here, and it will help you draw the equations of asymptotes. But I would like to just go charging right into it and show you a process that's going to help you figure out these asymptotes no matter where they are, okay? What I'd like to point out, however, is that in this first parabola that's centered on our screen right now, it's concave in the x direction, which means that the first denominator in the top left corner of your screen, right, we see this equation. The first denominator is an a squared, and in the horizontal direction, we're seeing the a value show up there, and we're seeing it show up here. So again, it's the distance from the center to a vertex. And we said that c was the distance from the center to the foci, but we didn't know what to do with, excuse me, we didn't know what to do with the b value. Well, now we know what to do with the b value. We're going to draw this vertical sort of distance up, and we're not going to draw it there. Really, we're going to draw it out of the vertices in the vertical direction in this case, up and down, and that allows us to create this box. And through this box, we can draw these asymptotes. And the asymptotes are there because a hyperbola only looks a little bit like a parabola. But a hyperbola actually goes out and follows along a pair of asymptotes every time. So we do need to have the ability to draw those asymptotes with some accuracy. Now the a value was the horizontal distance to the vertices, and the b value was going in the vertical direction. In our second diagram, it's the b value that's in the horizontal direction, and the a value that's taking us vertically. So we have to be careful with this. Either that, or we need to, as frequently as possible, disregard all the a's and b's and just use our brains and see if we can't crank out some right answers. So let's move briskly through this process of completing the square. If you would like to pause at this point and try to complete the square yourself, as we did at the end of the previous section's video, I welcome you to do that, and then you can compare what you get to what I get. Otherwise, I won't talk a whole bunch. I will just sort of churn through this. What I'll point out, though, is that notice that the y squared term here is positive, and the x squared term is negative. When we're working with a hyperbola, we're definitely going to want to put the negative squared term second, because the format for these equations, it's the second term that's the negative one. So we'll be prepared for that. So I will write the 9y squared first, and then the minus 18y, and then I'll leave a little space, and then we have a minus 4x squared plus 24x, and then we'll add in and leave a little bit of space, equals, I'm going to add the 63 over to the right hand side, and then we'll do our factoring. So this was just getting organized. Now we'll factor. And we'll take a 9 out of these two terms. y squared minus 2y. Here's where we're really going to be adding in that new value. And then here's where you have the potential to get tripped up. I'm going to factor a negative 4 out of these two terms. So here's the negative 4 that I'm reverse distributing away from the x squared. And when I factor a negative out of this positive, the sign is going to switch and it's going to become minus 6x plus something equals 63. And let's do it correctly on the right-hand side this time. We know it's coming. We're going to add 9 somethings, and we're going to subtract 4 somethings, something else's. All right, so whatever you can do, maybe I would highlight the negative 4, and I would highlight this plus sign and this minus sign. That's pretty important. And maybe this negative sign with the 4 over here on the right side of the equation. Those are the places where I think you're most likely to make your mistake in that process. So keep an eye out for those bits. Let's do the actual completing of the square. So we'll take the negative 2, divide it by 2, square it. That's equal to 1. That's going to go into this position and on the right-hand side of the equation, but not just yet. Here we'll take the negative 6, divide it by 2. That's 3 squared is 9. That goes here. And in the second position on the right-hand side, we're going to write them in this next iteration. So we have 9y squared minus 2y plus 1 minus 4 times x squared minus 6x plus our new value of 9 equals 63 plus 9 ones, and we're going to take away 4 9s. So I'm back on the left-hand side. Let's do some factoring. We'll write this as 9 times y minus 1 quantity squared minus 4 times x minus 3 quantity squared equals, on the right-hand side, 63 is made up of 7 9s. 7 times 9 makes 63. So here's 7 of them. We're adding another one in, so now we've got a total of 8. And then we're taking away 4 of them for a total of 4. 4 what's? 4 9s. 9, 18, 36. Now we need to divide both sides of our equation by 36 so that the right-hand side is equal to 1, just like it was with the ellipse. It must also equal 1 with the equations in standard form for hyperbolas. So divide the whole equation by 36. The 9 over 36 reduces, giving us a y minus 1. Yikes. Keep it together. Squared over 4 minus the x minus 3 is still here, squared over 4 reduces with the 36, leaving us with a 9 in the denominator and a 1 on the right-hand side. And we have the equation for our hyperbola that is not centered at the origin. The center of this hyperbola is located at, be careful, I'll give you a second. Tell me, what do you think the center of the hyperbola is? X coordinate is positive 3, y coordinate is positive 1. So I'm going to plot a point at 3, 1. And then, is the hyperbola concave up and down or left and right? Does it look like this or does it look like this? Since it leads with a y, it will be concave in the vertical direction, which means that the denominator under the y minus 1 squared, which is a 4, you take the 4 and square root it, that's equal to 2, and that will be the vertical distance to the vertices. So I'll start at the center, I'll go up 2 units and plot a point for a vertex, down 2 units from the center, plot a point for a vertex. Now you should put some kind of notes in there about what we just did. So maybe we could do this and say that the square root of 4 equals 2. We could say that concave, oh, it's tucked in behind me, sorry, concave up and down. We could also put a note that this 2 is the distance from center to vertex. Actually, it should be vertices, V-E-R-T-I-C. I don't know how to spell vertices. E-S? I'm pretty sure that's correct. Distance from center to vertices. Okay, so we've got those, and then, oh, that other denominator, the 9, this, square root of 9 is equal to 3, and 3 is going to help make the box. 3, I don't even know how to articulate that. Let's start drawing the box first. Maybe that'll give us a clue. So I know that my hyperbola is going to look something like this. Okay, I'm going to erase those, but it is going to look something like that. And let me actually draw this for you again. In order to make those happen, we're going to have some kind of a box in here that will have these diagonals that go through it, and those are going to be our asymptotes. So that's what we're trying to build. And in the vertical direction, let's see. Here we already have a distance of 2. But in the horizontal direction, we need to use this 3 that we found over here. So I'm going to start at the first vertex, the upper vertex, and I'm going to move 3 units to the right and put a point. And from that same vertex, I'm going to go 3 units to the left and put a point. Then I'm going to go down to this other vertex down here, and I'm going to move 3 units left and right from there, and put points at the ends of those. And then if you want to close the box, you can. You could put a vertical dashed line here and a vertical dashed line here. It's probably a good idea. But labeling this with a 2 and maybe labeling this with a 3. And then if you're a highlighter kind of a person, you know, you could highlight the 2 and the 3 and the 3, and the 2 is behind me over here. There it is. Highlight that 2. Right, just so you can visually, you know, cue your eye to train your mind to know that that's where those are used in drawing the graph. And now we can draw asymptotes. My family and some other people were kicking around some kind of a post about yardsticks. And I forget what the actual post was, if they're going to discontinue manufacturing yardsticks, or you won't be able to buy them like in person anymore or something. And my response, of course, was, who uses the yardstick anymore? When's the last time you used a ruler? I almost never use one, except for when I'm drawing diagrams for other people that require straight lines. Every once in a while I need a ruler. And what's fun about this one is this is actually an architectural tool. This is a scale, so it has basically has 6 different rulers on it that can help you draw lines and scale them up so that the diagram that you're drawing, or in an architectural case, you would be drawing a house or lot lines or something like that. You can draw them to scale so that the picture ends up being proportional when you draw it on a smaller piece of paper. And this belonged to my dad, so it's fun for me to use this. It makes me think of him. So I'm laying this through one of my diagonals, and then not with my highlighter, but with my purple pen. I'm going to draw myself my diagonal passing through here. I think I just wrote over one of my numbers. Let's take it as far as it'll go. Yep, there we go. Okay, and then in the other direction, I put the 2 and the 3 right in the wrong place for putting a ruler on there. See if I can skip over those. Now this is my kind of artistic ability. This suits my levels very well. Okay, so we've got our asymptotes in there. We know where the vertices are. I think we can draw ourselves a curve. So let's see if we can sketch this parabola in here. I think I'm going to increase my diameter of my pen so we can really see that it curves out and just goes along that asymptote, right? It doesn't actually ever touch. So see what you can do about making it look like it's getting close. Boy, these things get wide fast. I think of parabolas as, you know, usually being more like wine glass shaped. Yeah, maybe they turn into something that looks a bit more like a bowl, but ultimately I always know that they're going to be coming up. These things, though, they're staying pretty wide. Okay, let's get the lower half of this hyperbola in here. Decent. I always try to come out of those points almost horizontally. Too fast. That's nice. All right, we've done it. We have hand-drawn, using asymptotes, a hyperbola. Now, let's go one step further, because you will be asked to perform this task. I want to write the equations of the asymptotes. I want the equations of those lines, dashed lines. Let's see, where can we fit that? Maybe over here. We'll talk about asymptotes. So in order to write the equation for a line, you need a point on the line, the coordinates of a point on the line, and you need to know the slope of the line. Well, we know the coordinates of a point on both of the asymptotes. They share a point, and it's the center of our hyperbola, which is 3, 1. So we're going to be using x1, y1 will equal 3, 1. Perfect. And I might label these asymptotes. Let's label the bottom one L2 for line 2, and the one that goes up and to the right will be L1. And the slope of line 1 will be M1, and M1 is equal to, remember, slope is still equal to rise over run. That hasn't changed. I'm going to go from my center to this point up here at the top right corner of my box, and how do I get there? I have to rise 2 units, and then I have to run horizontally 3 units. So what do you think the slope of line 1 is? I think it's 2/3. Rise over run. Old school, not rocket science. Don't make it into rocket science. So we had a rise of 2. How do you say 2 and write 3? 2/3. If you want to draw that line and circle that little sort of part of a triangle right there, you're welcome to. Don't have to. I'm leaving it there, though. What else? Oh, yeah, we need M2. M2. All right, so to find M2, I'm going to come in here. I'm going to start at my center, and I'm going to go to this point at the bottom right corner of the box. And so I have to go rise down 2 units, run 3 units in the positive horizontal direction. So M2 is equal to -2 on the rise divided by 3 on the run. And that came from this. All right, that's starting to look pretty sloppy. Let's write equations for some lines. I know that y minus y1 is equal to m times x minus x1. That gives us, for line 1, we have y minus 1, because that was our y-coordinate of the point that we're using, is equal to m, now let's use m1, so that's 2/3, times x minus our x-coordinate of 3. Perfect. So that's your equation in point-slope form. We could make it into slope-intercept form. Maybe I'll do that over here. I have y minus 1 is equal to 2/3 x minus 2, distributing multiplication by 2/3 and simplifying. Adding 1 to both sides, I end up with y equals 2/3 x minus 1. So there's an equation of one of your asymptotes. For line number 2, we will use the same y1 value, a different slope, negative 2/3 this time, times x minus our same x1 coordinate. And from here, I want to follow the same format, so I guess I'm doing this one in the margin also. Let's distribute multiplication by negative 2/3. So we have y minus 1 equals negative 2/3 x plus 2. That's where the difference happens. When we distribute this multiplication by negative 2/3 and it hits this negative 3, the double negative turns into a positive, and the 3's cancel, so leaving us with a positive 2 there. And then we add 1 to both sides, and we get y equals negative 2/3 x plus 3. And there's the equation of your other horizontal asymptote. That could be a problem in and of itself. I don't know how much information I would want to give you and then just ask you to write equations for the asymptotes. I suppose with this sort of standard version of the equation, you might still want to draw a partial diagram. You might even still want to draw the rectangle. Obviously, it's easy to extract the center from that equation, and then the 4 is under the y, and the square root of 4 is 2. So you start at the center and you go up and down 2. Those are the vertices. And then in the x direction, you need to go side to side 3 units, because 3 is the square root of 9. You do that from either of the vertices and you got yourself your rectangle. Then I would still maybe sketch in the actual asymptotes. You could pull out a debit card or a student ID or something in order to help you draw those if you're drawing them relatively small. And then just use rise over run. You've got the values, right? 2/3. I mean, there they are, right? They're not hiding from you. It's pretty obvious. And we know that the 2 and the 3 came from the square root of the 4 and the 9. So do some practice problems. You're going to need to spend some time with these until you know them as well as I do. There's a lot of little nuances and facets and details and that kind of stuff. So make sure you're getting good sleep and staying hydrated so you get your wits about you. So while you're tackling these problems, you can get some right answers. Thanks so much for hanging with me for this conversation about hyperbolas. I hope all goes well, and don't forget to ask your professor lots of questions about little details and ins and outs of how to solve additional problems related to these equations. And I do still recommend that you try to, in your mind, relate the equation of the hyperbola and the ellipse to each other. I think that the differences between them can help you remember how to work and interact with the two of them. All right, that's it. I'm out of here. If you're ready for the next section, you can click on the link that's directly below me. Either way, I hope to see you soon. Thanks so much.